What is going on, Math 1? This is Mr. Bainey, and the lesson we're looking at today is 9.2, and Data Distribution and Outliers is the title. The essential question is, what statistics are most affected by outliers, and what shapes can data distributions have? So that means that we're still going to be calculating our statistics. That's the measures of center and spread that are from the previous lesson, and also how outliers affect those numbers, or at least we'll be able to look at how do we find outliers because we have a more precise way to do so. And then we're going to look at ways that we display data because it talks about the shapes of data distributions. So we have a few different types of displays, and the main one we're going to be looking at here is a dot plot. We'll look at more in the next lesson. A dot plot is also called a line plot. You could also call it an X plot because they use a number line, and we put X's or dots above the number line to show how often it happens. So if we look at, for example, this data that's right here, the 12 employees and their annual salaries in thousands of dollars. So we got 25, 30, 35, and so on. So all of these 12 numbers, we're going to display it into one of these data sets, and you can see here that it looks like it goes by fives, increments of 5. So we want to use this middle one right here. You can take a look at why we would not use the other ones, because we want all of the data values to be shown on the number line by one of the marks. So let's go ahead and create it here on the bottom. So I got 20. Next one is 25, then 30. As you can see here, I'm going to skip each mark and go by tens. So that way all of my increments of 5 there have its own mark. So I'm going to just look at the data that's right up here. So 25, 30, 35, 35, 35, 40. All of these numbers, I want to see what's the frequency of each one. And I'm going to put an X above that number on the number line with that frequency. So 20 doesn't show up at all. 25 shows up one time. So you can see I put an X there. 30 shows up one time. There's an X. 35 shows up 3 times. And so does 40 3 times. Then 45 shows up twice. Then 50 once and 60 once. Okay, 55 doesn't show up there at all. So you can see that this data on this dot plot has some sort of shape to it. The shape that I'm talking about kind of looks like this. Okay, always think of it as kind of like a hill sort of thing, where the top of the hill may be in the center, maybe on the side, on the left side or the right side. Okay, some things to pay attention to. Okay, and with that, we're going to go straight to how do we identify outliers. So if you are unfamiliar with what that is, it gives you a definition of an outlier. And in this box right here, we have a very specific mathematical way to find an outlier. So we have 2 formulas. So this formula that's right here in red is what we're going to test for the lowest value. Okay, if we feel like the lowest value is an outlier, we'll use that formula. And then we're going to use this formula if we feel like the biggest value looks like it's an outlier. Okay, so this is more or less a test to see if it is or isn't an outlier. And only the biggest or the smallest value can be outliers. No numbers in the middle can be outliers. Okay, so let's take a look at part B here at the bottom, page 390. And looks like we have a very similar set of data to the previous page, but I don't think it's exactly the same. So I'm going to label, I'm going to be labeling this exactly the same way as the previous page because there's very, very similar numbers. So 20 doesn't show up. There's a 25, a 30, there's 3 35s, there's 3 40s, there's 2 45s, a 50, a 60, and a 65. So it looks like the same data except that 65,000 has been added onto that. Then what we're going to do with this is what looks like an outlier. So we want to know, is this an outlier or is that an outlier? Which one is most likely? It is possible that they both are, but it's sufficient to just test the one that you think is the outlier. The one that looks more like an outlier, if it ends up not being one, it's probably safe to not have to test the other one, if that makes sense. So we're going to test the last one there, 65. So what I want to know is 65 an outlier. And the way we do that is, and by the way, it's the biggest value. So if you look all at the top here, the one I have in blue, the greatest value is going to be X. X is the data value I'm testing. I want to know, is it greater than Q3 plus 1.5 times the IQR? Okay, so let's try to write that down. I want to know, is it bigger than Q3 plus 1.5 times IQR? So in order to test it, I'll put a question mark at the end here because I'm not sure. I need to know what the Q3 is, and I need to know what IQR is. So I'm going to look at my list of data up at the top, and it is, looks like it is in order. So let's go, there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I do have a middle number. That's my median, my Q2. But I don't need to know Q2 for IQR. I need to know Q1, which is here. Q1 is 35. And Q3 is 47.5. Okay, it's halfway in between 45 and 50. If you're not sure how I got those, make sure you practice from the last lesson or watch that video, lesson 9.1. Okay, so I'm going to plug in these numbers here. I got 65. I want to know, is that greater than 47.5 plus 1.5 times the IQR? I didn't even find the IQR yet. It is, IQR is 47.5 minus 35, right? Q3 minus Q1. So that gives me 12.5. Okay, and give me a few seconds here. I'm going to calculate this. And I get 47.5 plus 18.75, which leads me to 65 is greater than 66.25. So this is actually a false statement. And because it's false, that means 65 is not an outlier. If it is an outlier, it would be bigger. Okay, so essentially what this formula is testing is 65 far enough away? Is it bigger than Q3 plus this extra number that we're adding on top of Q3? So is it far away enough from Q3? And in this case, it's not far enough. It's almost, really almost there. So let's try your turn, or have you try. Go ahead and pause it once I get there. Number 3, what you're going to do is first create a dot plot, and then you're going to test to see if there's any outliers. So what's going to make this a little bit easier is if we put this in order. So I'm going to do that first. I got 72, and no more 70s. I got 80, 81, and I'm going to pause this for a sec. The numbers are going to pop up. And here are the list, the numbers in order on the right side. I've drawn 2 different displays of dot plots that we could work with. Each of them has its own advantages and disadvantages. So you can sort of guess, not guess, but you can think for yourself as to which one you think you'd want to use. What the book's going to show is the one that's on the top, so that's this one right here. It is very, very tedious, as you can see here. I tried my best to make this accurate, but I went by ones. You kind of have to, because there's no clear pattern here. Like with the previous data, I went by 5s. So I didn't label every single one because it would just be way too crowded. So I was going by 2s, but you can see that I still have a tick mark for every single number that's in between 72 and 100. Okay, but I didn't label everything, and that's okay. You don't have to do that. Just label it enough so I know, so that I know, what number goes where. And you can see here, we call these intervals right here. So 72 to 75, any numbers that are 72 to 75 would show there. Any numbers that are 76 to 79 would show there, so we don't have any at all. Now 80 to 83, we have an 80 and we have an 81, so I'd put 2 X's above that. Okay, so I'm going to show what the dot plots look like, what both of these look like when they're completed here in a few seconds. And there are the completed tables. You can see that one is a lot more spread out because I didn't use intervals. That's the top one. And these ones are more bunched up because I used intervals in that case. So now let's go ahead and test the outliers. So I want to know, is 72 an outlier? So I'm just actually going to write it up here first. So outliers question mark. So we'll test them. 72 and 100. I want to know if they are. So 72 is our smallest number, and I want to know, is it less than Q1 minus 1.5 times the IQR? Okay. I'm going to first figure out what Q1 and Q3 to help us get the IQR, and then we'll also test 100 as well. So my Q1 is 81, Q3 is 90, and that gives me an IQR of 9. As I continue to go through this formula here, I got 72. I want to know, is that less than, forgot to put a question mark at the end there, is it less than 81 minus whatever 1.5 times 9 gives me? Okay, so that is going to be 13.5. So 72 is less than, or is it less than 81 minus 13.5? And it looks like it's not going to. That's going to be too small for us. So 72 less than 67 minus 5 is false. Okay, and I'm not going to show a ton of work here, but I'm going to get, for 100, if I want to test to see if 100 is an outlier, I want to know, is it bigger than Q3 plus 1.5 times our IQR? So that means, my question mark, 100, is that bigger than 13.5 plus 90 is 103.5, which is false. Okay. So I have barely any space here, but we have no outliers in this data set. Everything is close together enough. What outliers are going to do is that it is going to pull our measures of center to one side or the other based on how much of an outlier it is, right? So that's why we're testing for them. We could potentially take out the outlier if we think it's affecting our data in a negative way. Okay, and the next thing that we're going to do is be able to compare data sets. And it shows you how to do this on a graphing calculator. The calculators I have in my classroom, the yellow ones, do have this feature and pretty much follow the same steps. So you can take a look at how you do it on my calculator. If you have another calculator that you would like to learn how to do this or not sure if you can do this, just come in and see me and I can let you know after I'm just playing around with it for a minute or so. But I do want to show you some data here, or some statistics of what these numbers mean or what they represent. So we have numbers from the NFL in this case, and we also have some numbers from MLB, that's Major League Baseball. Here are the data values up here that were used. So these were used to calculate measures of center and the measures of spread for each of the data sets, right? We got 2 data sets, NFL, 1 for MLB. So you can think about if the NFL has a mean or median, or these are the ages, they're average ages, that's what they mean. So here is the measures of center for the ages in the NFL, measures of center for the ages in the MLB. Okay, so you can start to think about what that tells us. Okay, measures of spread, well, 0.6 and 0.46 for measures of spread, that's IQR and standard deviation, compared to 1.10 and 0.91. Okay, it gives you an explanation down here of what the measure of center from both the football and baseball leagues tell us and what the measures of spread tell us. Okay, that's how we're going to be using this data. So I am going to put some numbers here. Actually, I'm going to do the your turn. These ones. If you would like to, before I put these numbers up and start to talk about what these numbers are telling us, if you would like to either try this in your own calculator, or if you want to do it manually yourself, take the numbers from Illinois and from Arizona. It's the age of each member of Congress that are in both states. You can see Illinois has a ton more, but the number of data values is not really going to matter, because when we calculate mean, median, and then also our spread, we still get just single numbers for those. So the number of data, we could talk about that, but we'll be able to still find all of our measures. Okay, so they're all going to pop up here in a few seconds, and we'll talk about it, or I'll talk about it. And here are the numbers of measures of center and spread for both states. I'm going to first talk about the mean and the median. These are the measures of center. So for Illinois, it has the higher mean, but Arizona has the higher median. Now this is going to be a little bit inconclusive for us. These are ages, remember, the center of the ages. So like the average age of a member in Congress. So we can't really say much here. We could say that if we think the mean is more accurate, that Illinois has, on average, older members of Congress compared to Arizona. If we think median is more accurate in this case, then Arizona has older members on average. Now, since they're both different when we compare them, we can say that maybe Illinois or Arizona has some outliers that are affecting it and making this happen. So we're not quite sure unless we test some outliers. So we're not going to do that quite yet, but you could, if you would like to see if there are any outliers, you can certainly test that and make conclusions from there. I'm going to go on to talk about the spread between these two data sets, and this one is a very clear Illinois being the higher spread, and that means that Arizona has their range of their ages are closer together compared to Illinois. They're a lot more spread out. And so you can look at the youngest that's in Arizona is 26. The oldest looks like 58. Okay, and then in Illinois, the youngest looks like 24, maybe. Ooh, 22. And then the oldest, 71. Looks like the oldest, so much bigger range. It just means all of these data values, all these ages are more spread out, and that's why you're getting the bigger numbers there. So you can, use that information to explain. You're gonna write. You're gonna be expected to know how to communicate that. So I'm giving you a lot of different ideas and things that you could write down or say. And the next thing that we're going to look at, the last thing, is data distributions. On the bottom of this page, you're going to see we have 3 different types of pictures here. These are all dot plots. So you see a dot plot here, here, and here. Symmetric means that it's going to be almost like we can call this kind of like a bell-shaped type of curve. And then skew to the left means that we got more data here on the right side. Okay, that confuses me even. So keep that, hopefully that makes sense to you. Skewed to the right means that we have most of the data on the left side. Okay, and I'm not going to actually do this your turn here, or the example B, but you can take a look at the example that's right above here. So you can see that team A, it looks like this right here, is pretty symmetric. Team B is skewed to the left because we got more of the data on the right side. So you can see skewed to the left explains it. So read these explanations down below in preparation for your homework assignment that you're going to work on, and hopefully that makes sense to you. If you want to give part B a try and come in and check in with me, then of course you're always welcome. But take a look at what's below here underneath the dot plot and see what sorts of explanation they're looking for. Okay, and that's going to do it for this lesson. Thank you so much for watching. I hope it was a help to you. Come in and see me anytime for some additional questions you have. There's a lot of information in this lesson. All right, have a great day.